Thank you. One of the things I've noticed when I give demonstration lectures is that the most popular demonstrations seem to be the ones that involve explosions. So I thought we'd have a lecture entirely about explosions and explosives and the science behind them. Now, just before we begin, I do want to say that you should not try to replicate any of these experiments at home, and also please don't try to make explosives at home. As you'll see in this lecture, when explosives detonate, they do so extremely quickly, much faster than your human senses can respond to. In other words, explosives are very unforgiving, so please don't make explosives at home. Okay, so we'll begin the lecture then, of course, by creating an explosion. What we're going to do is to recreate, on a smaller scale, the largest explosion that ever happened on the surface of the Earth in recorded history. And it happened in 1883, and it happened on the volcanic island of Krakatoa. And there was an explosion which was equivalent to roughly 200 million tons of TNT. The shockwave travelled around the Earth 7 times. The bang was heard 3,000 miles away. Now, there's a theory about how the explosion occurs, and it goes like this. The volcano had been erupting and throwing out lava, and it left behind a gigantic underground chamber, and seawater rushed in and filled the chamber. Now, the walls of the chamber were very hot, the seawater turned to steam, the pressure built up, and eventually there was an explosion. So we'll try and create that effect on a slightly smaller scale here in the lecture theatre. So this is a glass tube that contains 1 millilitre of water. If we just bring the camera up on the screen, you can have a look at this. It's been sealed at both ends. It contains just 1 millilitre of water. What I'm going to do now is to heat it up and raise the temperature with this Bunsen burner. And as the temperature rises, the water starts to evaporate and the pressure begins to build up. And at some point it will explode. It will be quite loud, so I'm going to wear ear defenders, and you may wish to cover your ears for this one. Now, it's a little bit hard to know exactly when it's going to go. So this is 1 millilitre of water. When Krakatoa exploded, it's thought that around a cubic kilometre of water was turned into steam. So the water's turning to steam, the pressure is building up, and eventually it reached the point where the strength of the container is not sufficient to withstand that pressure, and that's when we get the explosion. So we call this a physical explosion. Explosion caused by a build-up and then a sudden release of pressure. All right. Okay, so that's an example of a physical explosion. The build-up and then the sudden release of pressure. Now, if we want to make an explosion for some practical application, this isn't very convenient. We have to have the flame, we have to wait for the pressure to build up, we're not sure exactly when it's going to go off and so on. We need a different way of creating explosions, and we're going to do that using chemistry. And so we're going to have chemicals that explode, we call those explosives. Now, for around 1,000 years, there was only one practical explosive which was known, and that's gunpowder. And in the trade, we refer to gunpowder as black powder. They mean the same thing. Now, gunpowder is just a simple mixture of 3 ingredients. And we've got the ingredients here. We can bring the camera up. This is the first one. This is charcoal, familiar from barbecues and so on. It's finely powdered. This acts as a fuel. We have sulfur, one of the elements, this lovely yellow powder. This also acts as a fuel, and it helps to promote the burning. And a very important ingredient is this one. This is potassium nitrate, also known as saltpeter. We can think of this as a very concentrated source of oxygen. So when this gets hot, it gives off oxygen, and the charcoal and the sulfur can burn in that released oxygen. So the fuels, the charcoal and sulfur, don't burn with the oxygen of the air, they burn with oxygen released from this very concentrated form of oxygen. So let's have a look at some gunpowder. In this dish I have 1.5 grams of a commercial gunpowder, and I'm going to ignite this electrically. There's a little device in there called an electric match. It looks just like an ordinary match. But I can set it off by passing an electrical signal to it, and I'll do that using this box. This is called an exploder. By the way, this is not called a detonator. We'll find out what a detonator is later on in the lecture. That's something quite different. So I'll charge this up, and then we'll set off 1.5 grams of gunpowder just in the open on the bench. As you can see, we have a lovely smoke ring. It burns very quickly. But you notice we didn't get a bang. We didn't get an explosion. Gunpowder is what we call a low explosive. When we set it off in the open, it burns very rapidly, but it doesn't give us a bang. It doesn't explode. To get an explosion, we need to do something else. We need to confine the gunpowder. And so that's what we're doing over here. In this cardboard tube, we have, again, 1.5 grams of gunpowder, the same quantity of the same type of gunpowder. Again, there's an electrical match inside the tube. But this time the tube is sealed, it's bound up with tape, and so the gunpowder is very tightly confined. Now what happens when we confine the gunpowder is that as it burns, it produces energy in the form of heat. The heat can't escape as it can on the bench, instead it's trapped. And so the temperature rises. And when the temperature rises, the rate of chemical reaction, the rate of burning increases, and that increases the rate of heat production, and so on, and we get this feedback leading to very rapid combustion. We call that an explosion. So again, we'll set this off electrically, and we'll use a different exploder this time. We're going to use this machine. This dates from the early part of the 20th century. It's a DuPont blasting machine. It's a genuine antique blasting machine, and remarkably, this still works. So we'll use this to set off the explosion. And at this point, I wonder if anybody would like to volunteer to come and use this. I think you were the first. Would you like to come on down? Let's have a hand for a volunteer, please. Would you like to come and stand there? Just not yet. Just turn around. Just face the audience. What's your name?
Isaac.
Isaac. Do you know how to use this? Have you seen this on cartoons? What do you think you do? Okay, what you do is you're going to take hold of the handle with both hands. Not yet, but when I tell you, you're going to raise it up. Okay, and then when I tell you, you're going to push it down nice and firmly. Okay, now this is going to be quite loud, so I'm going to give you a pair of ear defenders. You pop those on, and again, you might want to just cover your ears for this one. Okay, so when you're ready, off you go. Excellent. Thank you very much. Okay, so that's the effect of confinement on a low explosive like gunpowder. It accelerates the rate of burning, and we get that nice explosion. Now, gunpowder is just a mixture of fuels, sulfur and charcoal, and this source of oxygen, potassium nitrate. We call that an oxidizer. And people searched for alternatives to gunpowder, other kinds of explosives. And so they started to experiment with different choices of fuels and different oxidizers. And they invented a whole range of different explosives, and these are still used today in things like fireworks and pyrotechnics. I'm going to mention just one of them, and it's this one. It's called flash powder. And again, it's a simple mixture between a fuel, in this case a very finely powdered metal, and an oxidizer. Not potassium nitrate, but a different oxidizer, but again, a very concentrated source of oxygen. So I have 1.5 grams of flash powder, and it's called flash powder because it produces a very bright flash. It's used in the theatre, for example, when when the genie appears, you want a bright flash and a puff of smoke. So that's where you might use flash powder. So let's set off 1.5 grams of flash powder, and again we'll do this in the open on the bench. We'll bring the lights down for this, but it will be very bright. So I suggest you don't look directly at this, instead you look off to one side. So this is 1.5 grams of flash powder now, burning in the open. So again, it's very bright, and I suggest you look to one side. So here we go. So again, we had a very rapid combustion, but we didn't have a bang, we didn't have an explosion. But we know what to do to get a bang out of our flash powder. We need to confine it. So that's what we're going to do now. So this apparatus consists really just of a heavy cylinder of steel with a hole bored down the middle, and in the bottom of the hole we have, again, 1.5 grams of exactly the same type of flash powder. But now the confinement produced by the metal walls should accelerate the rate of burning, and again we should get an explosion. Again, we've got the electrical match, and we'll use our oldie blasting machine to set this off. So there's a chance now for another volunteer to have a go. Who'd like to have a go? Yes, on the end there in yellow. Let's have a hand for our volunteer. Let's come and stand there. What's your name?
Daniel.
Daniel. All right, Daniel, if you'd like to turn around. You saw what to do, didn't you?
Yeah.
So put those on. Wait for me to get mine on. This will be, I think, pretty loud, so again, I'd recommend that you cover your ears. Okay, off you go, Daniel. Lovely, thank you very much. Okay, so once again then, the confinement of this low explosive leads to an accelerated rate of burning, and we get an explosion. But people were constantly searching for ways to improve explosives to make them burn even faster. What could we do to make our explosives burn even faster? Well, the explosives we looked at so far are mixtures. They're mixtures between a fuel and a source of oxygen. And it seems obvious that the better we can mix them together, the faster they will burn, because they burn by the fuel coming into contact with the oxidizer. So we can test that idea out by using this. This is called lycopodium. It's a very fine powder, and it's flammable. So I'm going to put a little on a mat. We'll just see if we can set fire to this. And there it is. It's just about, you can just see a little flame. It's just caught fire. So this is flammable. What's happening is that there's a chemical reaction taking place. We call it burning, between the fuel, or the lycopodium powder, and the oxygen of the air. But it's a very slow chemical reaction because it only happens where the fuel comes into contact with the oxygen. It only happens at the surface of that little pile. So I'll blow that out. And what we can do now is try something different. We can take some more lycopodium powder, and this time we'll mix it very thoroughly with the air first, and then we'll set fire to it. So I'm going to put some more lycopodium powder into this tube, and I'll use the tube to blow the powder into the air. And that will mix the powder in the air very thoroughly. There'll be much more surface area of contact between the powder and the oxygen of the air, and that should improve the rate of combustion. So I'll use this Bunsen burner to set fire to the powder. We'll bring the lights down for this. And when the lights are down, I'll then blow the powder through the flame, and we'll see if that increases the rate of combustion. Okay, so clearly then, mixing the lycopodium more thoroughly with the air produced a faster rate of combustion. But using the oxygen from the air isn't very good because the air has a very low density. Each cubic metre of air doesn't contain very much oxygen. So we can do better if we use a more concentrated form of oxygen. So I'm going to use now liquid oxygen, minus 183 degrees centigrade. So this is just oxygen that's been cooled down until it turns into this beautiful blue liquid. In the dish, I have some ordinary cotton wool. So I'm going to soak the cotton wool in the oxygen. So the cotton wool will function as the fuel, but now we have a much more concentrated source of oxygen. And again, we'll bring the lights down for this. So this is cotton wool burning in liquid oxygen. So that certainly burnt pretty quickly. We got a little explosion there. But this, again, is not a very practical way to make an explosive because liquid oxygen, if we leave it sitting around, will warm up to room temperature and it'll evaporate. So it will just sort of disappear after an hour or two. We need something else, something a little bit more permanent. And the breakthrough came when a Swiss chemist, Christian Schoenbein, was doing some chemistry in his kitchen, of all places, one day, and he had a little accident. He'd been working with a mixture of nitric and sulfuric acids, which is a very corrosive mixture, and he spilled some on the kitchen table. And he reached for a piece of cloth to wipe it up, and it was a piece of cotton cloth. So he wiped up the acids with the cotton cloth, he hung the cloth up to dry over the stove, and when it dried out, it exploded, and he discovered some new chemistry. He discovered something called nitrocellulose, also known as gun cotton. And what was happening there was really rather special. The effect of the nitric and sulfuric acids was to introduce oxygen, and also nitrogen as well, into the actual molecules of the fuel itself. So the fuel is cellulose, these long molecules, a natural material, and the effect of the acids was introduce oxygen right into the molecule itself. So this is the best possible mixture we could have between the fuel and the oxygen, having them built into the same molecule. So let me show you some nitrocellulose. Thanks, Chris. So this is some that I made earlier. This is just ordinary cotton wool I could buy from the chemist, but it's been treated with nitric and sulfuric acids, it's been washed and dried, and it still looks and feels pretty much like cotton wool, right up until the point where I set fire to it. Now, this is actually going to be fairly bright, so again, you might just look slightly to one side. So this is nitrocellulose. Now, nitrocellulose, when it burns, produces relatively little smoke. We had quite a large pile of nitrocellulose, so we got hardly any smoke compared to the tiny amount of gunpowder, for instance. The gunpowder produces a lot of smoke because the products, the output, the end result of the chemical reaction includes materials like potassium carbonate, which are solids at room temperature. So it's those tiny particles of solid which make up the smoke. The nitrocellulose, the molecules rearrange themselves into things like water vapour, carbon dioxide, nitrogen gas, things which are invisible gases present in the air anyway, and so the nitrocellulose more or less seems to disappear. So nitrocellulose is used a lot in pyrotechnics, partly because it produces very little smoke. It's a very convenient material to use. And so what I'm going to do now is put on a little pyrotechnic show for you, and I hope you'll enjoy this. So we'll bring the lights down. So these are nitrocellulose pyrotechnics. Okay, so in all the explosions and the pyrotechnics we've seen, there is a sudden release of energy when the explosion occurs. So where does that energy come from? Well, we can gain some insight into this source of energy with a little demonstration. And for this, I'm going to need one very brave volunteer. So who's feeling extremely brave? Lots of people volunteering their friends. Who'd like to come on down and do this one? You seem very keen. You're very brave. Let's have a hand for our volunteer. If you'd like to come and stand just there and pop those on. What's your name?
Lucas.
Lucas. Right, Lucas, what I want you to do is hold out your right hand, arm's length, that's it, and I want you to form your hand into a little cup. Just one hand is fine, just a cup like that, that's right. This is just soap solution, it's just sort of washing up liquid really. And I'm going to put a little puddle of this in your hand. You did say you were brave, didn't you? Okay, there we go. So I'm going to create a little explosion in your hand. Now, this is an electrical power supply, and we're passing electricity through a bottle containing water. It's actually sodium carbonate solution. And the effect of the electricity is to break up the water. Now, water, let's just move that a bit closer. There we go. Water, of course, you all know the formula for water, H2O. Water is a compound of hydrogen and oxygen. And the effect of the electricity is to break up the molecules to produce hydrogen gas and oxygen gas. So this little pile of bubbles in your hand contains a 2-to-1 mixture of hydrogen and oxygen. Okay, I think we'll just have a little bit more there. How brave are you feeling? Quite brave. You're feeling a bit nervous? Okay. I'm not nervous. Right, we'll switch that off. Now, we're going to pop some ear defenders on you for this. Thanks, Chris. Thanks very much. I'm going to pop some ear defenders on. And we'll set fire to this mixture of hydrogen and oxygen. You ready? Hold your arm up straight. Here we go. Well done. Okay, thanks very much. Okay, you're back to your seat now. Okay, so that little explosion clearly released some energy, but where did the energy come from? Well, hydrogen gas consists of molecules, and each molecule contains a pair of hydrogen atoms like this. Now, oxygen is similar. Oxygen consists of oxygen molecules, and each molecule again has a pair of oxygen atoms. Now, our volunteer's hand had some bubbles. Inside the bubbles, we had a mixture of 2 parts hydrogen and 1 part oxygen. But it just sat there. It didn't do anything until we applied a flame. When we apply a flame, we're adding a bit of energy. We call that activation energy. It's a very important concept. The activation energy is breaking apart the molecules. It's breaking the bonds that hold the molecules together. We have to put energy in order to break those bonds. So the bonds of the hydrogen and oxygen get broken, and then new bonds can form. The oxygen and the hydrogen can come together to form water. So as they come together to form new bonds, energy is released. And a lot more energy is released by the formation of these new bonds than it cost us to break the original bonds. And so with 2 molecules of hydrogen and 1 of oxygen, we can make 2 molecules of water. So this is water H2O. So this idea of activation energy is a very important one. I can illustrate it with this model of a ball on a hill. So the ball is at quite a high point on the hill, so it has gravitational potential energy compared with the bottom of the hill. Energy would be released if the ball could roll from the top to the bottom of the hill, but it can't because it's stuck in this little well, this little valley. If I add a little bit of energy to this, nothing much happens. But if I add enough energy to get it over the hump, and we call that the activation energy, then the rest of the energy can escape. I get the activation energy back again, plus all this extra energy. So when we set fire to the hydrogen and oxygen, we are adding the activation energy, and then we get the activation energy back again, plus a lot of extra energy. So that's the idea of activation energy. Now I'm going to illustrate activation energy with a different kind of experiment, and for this we're going to bring the lights down because we're going to use not heat as the source of activation energy, but rather light. So we're going to do an experiment now which involves a glass tube, a heavy glass tube, filled with a mixture of hydrogen gas and chlorine gas. Now again, the 2 gases are sitting there mixed together, nothing very much is happening. But if we apply some activation energy, we can break apart the bonds of the molecules and they can react to form hydrogen chloride and at the same time release some energy. So we're going to use light to provide the source of activation energy. Now light consists of particles called photons, and the energy of each photon depends upon its colour. In other words, it depends upon its wavelength or its frequency. So long wavelength light, such as this red light, the photons have a relatively low energy. So what's happening now is the red light from the projector is passing through this tube which contains hydrogen and chlorine, but no reaction is taking place because the photons don't have sufficient energy. At this point I'm going to put some ear defenders on and then we'll explore some different wavelengths of light. So let's go to a higher frequency or shorter wavelength of light. We'll try some yellow light. Higher energy, but still not enough to get the ball over the hill, not enough to reach the activation energy. There's some green light, higher energy still, but not still quite enough energy to get over the hill. But let's try the shortest wavelength of all, some blue light, where the photons have the highest energy. So that's an example of activation energy. We add a little bit of energy to get the reaction going, and then it releases a lot more energy. Now, different reactions will have different levels of activation energy. Sometimes that hill at the top will be quite high. That's a high activation energy. We need to put a lot of energy in to get the reaction going. Sometimes the activation energy will be very small. I'm going to show you a reaction now where the activation energy is so low that the reaction happens spontaneously. What I'm going to do is to add this grey powder, it's called magnesium silicide, to some hydrochloric acid. Now, the reaction that takes place produces a gas called silane. Now, you've all heard of methane gas, I'm sure. Methane is natural gas. It's the gas that you use for cooking and so on. And a molecule of methane has a carbon atom and 4 hydrogen atoms. Well, silane is very similar, except that it has a silicon atom and 4 hydrogen atoms. And like methane, it will burn in the air, but the activation energy is so low that this will ignite as soon as it's formed. So we'll bring the lights down for this. I'll add the magnesium silicide to the hydrochloric acid, and as soon as the silane gas is formed, it will ignite in the air. Okay, so that's a system with a very low activation energy. What I'm going to show you now is an explosive that has a very low activation energy, not so low that it goes off spontaneously, but almost. This is an explosive called nitrogen triiodide, and the molecules consist of nitrogen bonded to iodine. But the bonds are very easily disturbed, and when that happens, an explosion takes place. Now, this will be quite a loud explosion. So again, I'm going to wear ear defenders, and you may wish to cover your ears. The nitrogen triiodide is this black solid sitting here on this filter paper. All I'm going to do is to give it a gentle tap with this stick, and that should be sufficient to set it off. So here we go. Now, I'm sure, all being observant scientists, you'll have noticed that cloud of purple vapour that's produced. That's iodine. So the molecule consists of nitrogen combined with iodine. It breaks apart to release the iodine and nitrogen. Now, nitrogen plays a very important role in explosives, and I'll explain why that is with the help of this model. This is a model of a molecule of nitrogen, and it consists of 2 atoms of nitrogen joined together by this very strong triple bond. Now, this is one of the strongest chemical bonds in the whole of chemistry. It means that nitrogen is a very unreactive material. So nitrogen, as you know, is about 4/5 of the air. And it's very hard to get the nitrogen in the air to react with anything. That's because the bond is very strong. So to get the nitrogen to react, we'd have to pull the atoms apart and break this very strong bond. That would require a great deal of energy. Now, energy, of course, is conserved. So if we took 2 atoms of nitrogen and brought them together so that this bond is formed, that same amount of energy must be released. So when nitrogen gas is formed, a lot of energy is released. And that was what was happening with that nitrogen triiodide. A lot of that energy was coming from the formation of this nitrogen-nitrogen bond. So nitrogen plays an important role in explosives. There's a very similar explosive, a little bit less sensitive than nitrogen triiodide, which plays a very important role because it saves many lives every year. It's used in car airbags. Now, a car airbag, as you know, is a safety device where a bag is inflated moments before, as a collision is occurring. When your car collides with something, the airbag is set off, and the airbag will protect you, hopefully, from injury. Now, I imagine that most of you have never actually seen, I hope most of you have never seen an airbag going off the reel. So what we'll do today is actually set one off for you. So we've got not a real car, but nevertheless a real steering wheel with a genuine airbag inside. And we have a battery. At the front of the car is a little switch. In a moment, I'm going to drive or push the car into the wall. It will close the switch and set off the airbag. This is actually quite loud. Obviously, if you're involved in a collision, the last thing you're worried about is a loud bang. But if I can find my ear defenders, I'm going to pop these on. And then we'll have a look at a car airbag. So here we go. Okay, so that's a car airbag. That contains an explosive called sodium azide. It's a compound of sodium and nitrogen. When it decomposes, or when it explodes, it produces sodium metal and nitrogen gas. And it's the formation of those nitrogen bonds that produces a lot of the energy of that explosion. Now, people searching for new explosives realised that Schoenbein's discovery of nitrocellulose, or gun cotton, was an extremely important one, because he had worked out how to introduce oxygen and nitrogen directly into molecules in order to turn them into explosives. And his first discovery was nitrocellulose, or gun cotton, but people took the same idea and began to search for other explosives in which nitric and sulfuric acids were used to introduce the oxygen and the nitrogen directly into the molecule. So people searched lots of different possible compounds, but the real discovery was made by an Italian chemist, Ascanio Sobrero, in 1847, when he tried nitrating, that is, treating with nitric acid, not cotton, but another substance called glycerine. Now, glycerine is a byproduct of the manufacture of soap, and if we nitrate glycerine, we get a substance called nitroglycerine. So this is some nitroglycerine. This is a small quantity which I made this morning here in the chemistry department, and you can see it's a clear liquid. It looks a bit like water, slightly viscous. You'll see in a moment it behaves rather differently from water. So what I'm going to do first of all is to place a few drops of the nitroglycerine onto a heat-proof mat, and we'll set fire to it and we'll see what happens. I'll put the rest of it away. And let's see what happens if we just heat this with a blowtorch and try and set fire to it. So I hope you saw there, it just burns. It burns with a lovely green flame. There's no explosion, just a very small green flame. It behaved a bit like the nitrocellulose. It burned very rapidly. But nitroglycerine can do something very different, and I can illustrate that in the following way. I'm going to take a filter paper and place it on this steel anvil. I'm now going to get the same quantity of nitroglycerine and place them on the filter paper. There we go. And this time I'm going to hit the nitroglycerine with a hammer. And the effect should be rather different from before. So this is likely to be very loud, so I'm going to put ear defenders on. I'm also going to put on a face shield. And I'm going to wear a glove. This is definitely one you shouldn't try at home. Okay, so this is just 5 drops of nitroglycerine. So what happened there was very different. In the first case, it just burned. But here, something very different happened. We call this detonation. And detonation is a very specific physical effect, and we'll have a look at that again in a moment. Now, nitroglycerine has quite a reputation for being a dangerous material, and that's because in the early days there were a lot of accidents when it went off by mistake, when it was being made or when it was being transported. And although nitroglycerine is an extremely powerful explosive, it wasn't a very practical explosive. It was just too dangerous to use. And this was very disappointing, and so people tried to find a solution. And the person who really solved the problem was a Swedish chemist called Alfred Nobel. And he tried combining the nitroglycerine with other materials in order to make it less sensitive. And one day he hit on this material. So this is a clay-like material. It's called kieselguhr. And kieselguhr is very absorbent, so it can absorb many times its own weight of nitroglycerine. And when it does so, it remains a very powerful explosive, but it's much less sensitive. And he called this material dynamite. And dynamite's usually made up into sticks, and the sticks can be pushed into boreholes in rock if we're doing quarrying or mining or tunneling. It's a very safe explosive because it's much less sensitive than pure nitroglycerine. And so it's safe to store and transport. So Nobel had solved one of the great problems with nitroglycerine. He'd worked out how to prevent it going off accidentally. But there's another problem with nitroglycerine, is that it doesn't always go off when you want it to. It's a kind of unreliable explosive. And when it's made into dynamite, because it's very insensitive, it's very hard to get it to go off. Setting dynamite off is actually very difficult. So that led to Nobel's other great invention, and this is called a detonator. And this is a modern electric detonator. It just consists of a small metal tube, and inside is a very small quantity of an explosive that's quite sensitive. We call it a primary explosive. So the explosive in here is quite easy to set off. This one is actually a modern detonator which is set off electrically. Nobel's original detonator would have been set off by a slow-burning fuse. Now, this was a brilliant invention because the detonator, although it contains a sensitive explosive, it only contains a tiny quantity of that explosive. So although detonators are quite dangerous things, there's a limit to how much damage a single detonator can do. So the detonator is kept well apart from the main explosive, the dynamite, right up until the moment that we want to use the explosive, and then the detonator is placed in contact with the explosive. The effect of the detonator when it goes off is to create a small explosion that provides a very sharp shock. It's rather like the hammer blow. And that hammer blow is enough to set off the main explosive. So the dynamite is safe because it's very insensitive. The detonator is relatively safe because it doesn't contain very much explosive. And those two inventions of Nobel really opened up the world of high explosives. And as a result, he became extremely wealthy. In fact, he became one of the richest people in the world at the time. And when he died, in his will, he gave his vast fortune to the creation of the Nobel Prizes, which are today the most prestigious prizes in science. And there's even one of the elements named after him. It's called nobelium. Now, dynamite was sort of the beginning, really. There were lots of other explosives invented. I'll mention one of them. If you take a solvent called toluene and treat that with nitric and sulfuric acids, you get trinitrotoluene. And the abbreviation for that is TNT, again, an explosive that many people have heard of. So don't confuse TNT with dynamite. They're quite different. Dynamite consists of nitroglycerine absorbed into kieselguhr or some other material, whereas TNT is a completely different chemical compound. And people continue to research new kinds of explosives. This is a very new one. This is the latest British explosive. This has been available for a couple of months now. This is a plastic explosive. It's called PE7. And a plastic explosive, an explosive that's squidgy and mouldable. So this is like sort of plasticine or Play-Doh. This is a very powerful explosive, but I should just say that none of these explosives are live. This is actually a training block of material. It's identical to real PE7 in every respect, except that the explosive component has been replaced by an inert material. And it's also been coloured blue so that you can tell that it's inert. The real explosive is white. So when we looked at the combustion of gunpowder, we saw that gunpowder in the open just burns. It burns very rapidly, but it's just a burning process. There's no explosion. When we hit the nitroglycerine with a hammer, we get something very different. We get this loud explosion. We call that a detonation. The burning of gunpowder and other explosives of that kind, we give that a fancy word. We call it deflagration. It just means burning. So low explosives burn, whereas nitroglycerine is something very different. We call it a high explosive, and high explosives detonate. I want to explain the difference between a low explosive and a high explosive and explain what's meant by detonation. So first of all, we're going to demonstrate this idea of deflagration or burning. So this is a metal track and it contains a powder. The powder is actually finely powdered nitrocellulose. It's the kind of powder that's used to reload the bullets for guns. And what I'm going to do is to set fire to this trail of powder at one end. And you can see what's happening. The trail of powder is burning along. What's going on here is that a pile of the powder is burning and releasing energy in the form of heat. That heat energy is raising the temperature of the next piece of powder, providing the activation energy so that it can burn. It then releases heat and in turn ignites the piece of powder to the next door to it. So what's happening then is the flame is progressing by the transfer of heat. So that's what we call deflagration. That's a low explosive. Detonation is something completely different. And to explain this, I'm going to need about 6 volunteers, something like that. Who'd like to come on out? Any guys in the front? Shall we have... Yes, come on, you guys come out. How about from you to there? 8 of you. Come on then. Let's have a handful of volunteers. If you'd like to form a row... Oh gosh, we could... Do you want to come to this end? Maybe if you come to this, if you come and stand just here, just trying to get to a roughly height order. Okay, that'll do. Right, what I want you to do is to face this wall. What's your name?
Tom.
Tom, all right. You just stand upright like that. Now, what's your name?
Bridget.
Bridget, okay. If you just stand back a little bit, face Tom's back, put your hands on his shoulders and grip them very tightly. If you just stand back a little bit, have your arms very rigid, locked rigid, that's good. So if I move you, he'll move, okay? So keep your arms locked and rigid. Okay, you do the same thing. What's your name?
Harry.
Harry, okay, put your arms on her shoulder, stand back a bit, keep your arms nice and locked so that you move together. Okay, same thing. What's your name?
Hugh.
Hugh, okay. You are?
Joe.
Joe.
Mark.
Mark, okay, put your hands on his shoulders, arms nice and rigid, so you're locked together, that's good. Oh, right, okay, can you reach? Put your arms on his shoulders. What's your name?
Kim.
Kim. And you are?
Abby.
Abby, all right. Arms on her shoulders, good. Now, what I'm going to try to do, keep your arms nice and rigid and locked. I'm going to give you a shove and we'll see what happens. Okay, I'm going to do that one more time. So when I give you a push, good, the push sort of works its way down. Now what I want to imagine is each of our volunteers is like a molecule in a block of explosive, and their arms are like the bonds between the molecules. If one of the molecules gets a push, or a knock with a hammer, then the wave travels through the block. Now if it's a block of regular material, that would travel at a particular speed. We call that the speed of sound. This compression wave travelling through a material we call a sound wave. It's how you're hearing my voice right now, through compression waves travelling through the air. And those compression waves, those sound waves, can travel through solid materials as well. Okay, let's have a big hand for our volunteers. I want you to imagine that this little dot is a source of sound waves. So those circles spreading out are sound waves. The light circles are regions of high pressure, and in between we have regions of low pressure. So that's sound waves spreading out from an object. Now let's imagine that the object starts to move. Well, you can see what happens. The sound waves ahead of the object pile up and get closer together, and the ones behind it are sort of trailed out and they get further apart. Now we call this the Doppler effect. It's something that's very familiar. If you hear a car go past, it makes a particular noise. It goes, meow. Okay, the note, the pitch, drops as it goes past you. And you can see why. Ahead of the object, the sound waves are bunched up, the wavelength is shorter, the frequency or the pitch is higher. Likewise, at the back, the waves are spread out, so the frequency or the pitch is lower. Now, what would happen if the object moved at the speed of sound? Well, here's the object now moving at the same speed as sound waves. And now the sound waves all pile up at the front of the object. They all catch up with each other. And so you get this region of very intense pressure. And let's just make it move a little bit faster than sound. And you can see there's these sort of bow waves. We call it a shock wave. That's where the sound waves are all catching up with each other. So that shock wave is something that would be produced, for example, by an aircraft when it's travelling faster than the speed of sound. So a supersonic aircraft would create this shock wave, and we can hear the effect of that shock wave on the ground in the form of a sonic boom. So a shock wave is the mechanism by which a high explosive detonates. So in a high explosive, it's not heat being propagated from one region to another, like in our trail of powder. It's not just heat energy raising the temperature of the next piece of explosive. It's rather the passage of a very fast shock wave, travelling much, much faster than the speed of sound. Okay, thank you for the computer screen. So how does a shock wave set off the explosive? Well, I can demonstrate that with this apparatus. This is a clear plastic tube, and it has a piston, a plunger, which is sealed. And I'm going to take some cotton wool. This is just ordinary cotton wool. It's not gun cotton or anything, just ordinary cotton wool. Take a little piece of this and place it in the end of the tube. And then I'm going to seal the tube. So what I'm going to do now is to compress the air in this tube. And I'm going to do so very quickly. Now, if you've ever pumped up your bike tyres quickly, if you're in a hurry and you pumped up your tyres really quickly, you'd notice that the tyres and maybe the pump as well get hot. So when we compress a gas, it gets hot. So I'm going to compress this gas very rapidly, and if we bring the lights down, we'll see what effect this has. So remember, there's just a little bit of cotton wool right there in the end of the tube. So here we go. So that got so hot that became so hot that the cotton wool actually ignited, and there's nothing left in there now, it looks like an empty tube. When a shock wave passes through a high explosive, that shock wave is a region of very intense pressure. And that pressure heats up the explosive and causes it to detonate. And that detonation releases energy, which is what drives the shock wave onwards. And that shock wave travels much faster than the speed of sound. Now, what I'd like to do now is to try to demonstrate for you a detonation shock wave here in the lecture theatre. Now, it's quite difficult because if I just set off a block of plastic explosive, that would be the end of the lecture. I can't do that, obviously. So I'm going to find a way of demonstrating a detonation. And to do that, I'm going to use some of this. This is called shock tubing. It's actually a commercial product. It's used on an enormous scale by the explosives industry, and it consists of a plastic tube, a hollow plastic tube, and the inside of the tube is coated with a very fine powder of a high explosive called HMX. And this explosive is about 70% more powerful than TNT, but there's just a very light dusting of it. So what I want to do now, if we can put the camera on screen, is to, let me just step back a moment. What I'm going to do is to blow through the tube and watch to see if you can see some of this HMX powder coming out of the tube. Okay, so it's just held on by static electricity, so I can blow it out of the tube. Now, if I just took a piece of shock tubing and set fire to it, it'd be rather like the nitroglycerine, it would just burn. But if instead we can provide a very sharp shock to the tube, we can initiate a detonation that will pass down the tube at very high speed. So let's have a look at that. And to illustrate shock tubing and show you how it works, I've got a little demonstration in which I've used shock tubing to spell out the name of the explosive that it contains. So this says HMX. And hopefully this will help you to remember the name of the explosive. So I'm going to initiate this shock tubing obviously with a shock, and that's going to be provided by this device, which produces a voltage of 2,500 volts, and then discharges it to make a little lightning strike, if you like. So I'm just going to point this at you, quite safe, and fire it. You should just be able to see a little spark. Okay, over here. I'll try over there. So it's not producing very much energy, but it's producing that energy in a very short interval of time in the form of a shock, and that can initiate a detonation wave travelling down the shock tube. So these letters consist of just a single length of shock tube wound in and out of the board, And so we'll fire the shock tube, and hopefully you'll be able to see the detonation of the tubing. Now, this will produce quite a bright flash, so if we bring the lights down, you should be able to see the shock tubing firing quite clearly. It makes a little bit of a noise. You may or may not wish to cover your ears. Okay, so here we go. This is shock tubing. Here we go. Okay, so that was a detonation wave passing through a few meters of shock tubing, but it's extremely quick, so I doubt that you could see the actual detonation wave pass along the tubing. So what I'm going to do now is to set off a longer section of shock tubing and see if we can actually see the detonation wave passing along the tube. And for this, I'm going to need 4 volunteers who'd like to come and hold the shock tubing while we set it off. Some of the hands are going down, I notice. We'll have you on the end there. And who else should we have? We'll have you, and yes, you can come on down, and let's have you as well. Let's have a hand for our volunteers, please. Okay, if you stay there. You stay there. If you come with me, to this end. You maybe. There we go. If you'd like to come and stand about here. Now we're going to give you some eye protection and some hearing protection, and we'll give you a glove to hold as well. And this is the shock tubing. So if you come with me, stand about there. What I want you to do, what's your name?
Albert.
Albert. Right, Albert. I want you to hold that end of the tubing. Just hold that for a moment. I'm going to wind this out across the full width of the lecture theatre. Okay, hold that. Just hold it in your gloved hand. What's your name?
Adam.
Adam. Okay. Now, if you'd like to come with me a little bit, hopefully there's enough to go all the way across. If you stand about there, hold that. And if you come with me, what's your name?
Bradley.
Bradley. And you're going to be down this end. All right, pretty good. You hold that there. What's your name?
Adam.
Adam?
Yeah.
Okay. What I want you to do, hold it nearer the end. Now, it's very important. I want you to point that away from your face, okay, because there'll be a little spit of flame come out of the end. Hold it up nice and tight. We're going to try and stretch this out. So if you step forward a little bit, hold it up nice and high so everybody can see. That's good. If you just step forward a little bit, that's good. And excellent. Good. Okay, so what we're going to do now is to start a shock wave, a detonation wave, at this end of the tubing, and we'll see if we can see it passing all the way down to the other end of the tube. So again, we'll bring the lights down for this. And here we go. 3, 2, 1. Head back to your seat now. Okay, just stay where you are for a moment. You just stay where you are. If you'd like to head back to your seat. So the 2 volunteers at the end can go back to their seats. Let's just thank them once again. Just stay where you are. You wait there. Okay, so, you may or may not think you saw that shock wave travelling down the tube, but I can tell you now that it was travelling at 2,100 metres per second. That's nearly 7 times the speed of sound. So you'd be quite lucky if you did actually see it. But I really wanted to show you a detonation wave. I wanted you to see a detonation wave passing at 7 times the speed of sound. So what we've done, and I think this may be the first time this has ever been done, is we've wound nearly a kilometre, there's something just over 800 metres of shock tubing wound around the walls of the lecture theatre. So we're going to bring the 2 ends out now to the middle of the lecture theatre. Thank you, Chris. All right, so you come with me. You're going to hold this end. Okay, that's it. You stand there. And you come with me. Now, we may overlap you a little bit. That's fine. Keep going. We've got a few knots in. That shouldn't matter. Okay, so I think this is a first. We tried a smaller scale demonstration earlier in the week. It was very interesting. So this is the first time we've tried it with such an enormous length of this shock tubing. So this should take about 0.4 of a second, just under half a second, for the shock wave to travel along this tube 8 times around the lecture theatre and then back along this tube, if it all works. And I hope you're happy. So you are completely surrounded by an explosive that's 70% more powerful than TNT. Okay, so here we go then. We'll bring the lights down. Let's hold it up nice and high. And we're firing in 3, 2, 1. So when an explosive detonates, of course, it produces gas. So we've now got 800 metres of tubing full of high-pressure gas. And if I bring that... You hear that gas escaping? Extraordinary. Let's have a big hand for our 2 volunteers. Thank you very much. Thank you. Okay, so that pretty much brings us to the end of the lecture. Obviously, it's a lecture about explosions, so of course we have to end with a big explosion. Before we do, though, I just want to say a big thank you, first of all, to the Department of Chemistry for hosting this. I'd like to thank our sponsors, of course, Microsoft Research, Event Horizon and Lemaitre for their very generous support. I'd also like to ask you to join me in thanking somebody who's put a lot of effort into helping me prepare and deliver this lecture, and that's Chris Braxton. Okay, so we need a good explosion to finish, and we're going to create another physical explosion. If you remember at the beginning of the lecture, we had that little tube of glass water which we heated up, the pressure built up and it burst. That was a physical explosion. So we're going to do something similar, but we're going to scale it up a little bit. And instead of using water, this time we're going to use liquid nitrogen. So this is liquid nitrogen. This is at minus 196 degrees centigrade. So nitrogen, remember, that's about 4/5 of the air. If we cool it down to minus 196 degrees centigrade, extremely cold, it becomes a liquid. So we have some liquid nitrogen here. And if we were to add liquid nitrogen to warm water, it would raise the temperature of the liquid nitrogen. It would evaporate and turn into a gas. And in the process, it would expand, rather like the water boiling and turning to steam. So I'll first of all demonstrate that by adding some liquid nitrogen into some hot water. Okay, so when we add the liquid nitrogen to the hot water, the liquid nitrogen turns from a liquid into a gas and it expands. And that's fine because it can expand and escape into the room. But what would happen if we did the same thing but we used a closed container, a sealed container? Well, the container that we're going to use is this. It's a half-litre fizzy drinks bottle. So I'm going to put some liquid nitrogen into here, screw the lid on so it becomes a sealed container. And of course, when you're taught how to use liquid nitrogen, you're told under no circumstances keep your liquid nitrogen in a sealed container. You'll find out why in a moment. I'm then going to drop it into here where we have a bucket inside. The bucket contains some warm water, so the nitrogen will evaporate and turn into a gas. It will like to expand, but it'll be trapped inside the bottle. The pressure will build up, and you can guess the rest. So let's get some liquid nitrogen. I'm going to fill this about 1/3 full of liquid nitrogen. There we go. So this is the final demonstration of the lecture. I hope you've enjoyed yourselves, and I hope you enjoy the final demo. Here we go.